For this session, everybody can be made panelists, so that there is more interactability. Am I audible?
Yes, ma'am, you are audible.
Okay. Okay. So can we start the session?
Yes.
Um, Harshit, please make all the attendees as panelists.
Is my screen visible?
Yes.
Okay. So let's start with the meta-heuristic implementation or neural network. For this, we again use the torch library and some modules of it. So as in previous session, we learned that we can optimize our parameters using meta-heuristic train-free methods. So we will employ two meta-heuristic algorithms like genetic algorithm and PSO, particle sum optimization on the neural network to get the best parameters for neural networks. So let's start with importing the libraries. So here the torch and torch.nn is a new thing for you. It is a module of torch library which import neural network module directly. So we don't have to define the model manually. And for this torch from this module dot functional, we will import f. This module have all the functions like loss functions, activation functions in this library. So we will directly import from there. And this is the sklearn library for load iris data. And this is sklearn library to train test this and standardize the data. So again, we do the same thing of loading iris data and split it in X and Y and normalize it. Then we will split in train and Y train because we only want to get the weight parameters. We don't want to test the model. So we will only define the X train and Y train and again test size and random state here. So we will convert the data into torch tensor to make it compatible for the neural network because we are using torch library here. And this torch.float32 is the standard type for neural network inputs. That's why we have taken it. And this torch.long will make the label vector as integer like 0, 1, and 2 only. It ensured it to make it compatible for the torch library. So I hope you able to understand these things. And now we will start the neural network architecture. So first, the class of neural network we define. NN dot module is already defined in the library. First, we initialize this class with the self variable. If you remember, the self variable will take all the variables of class, and because this net class is defining from a parent module NN dot module, so we have to initialize the parent module class. Again, initialize function is called. So we will define the layers of the neural network. NN dot linear means the layer will be linear one-dimensional layer, and ST1, this is the first layer. So because iris dataset has 4 features, so the first input layer has 4 neurons, and the one middle hidden layer has 8 neurons. We can change it, and again the output layer, the third layer, has 3 neurons because we have 3 classes in iris data. So this will create the matrices of 4 cross 8, 8 cross 8, and 8 cross 3. And now we will define the forward function in this neural network class only. And forward function will call only the data parameter x. So x will assign the ReLU function in the first layer. So the ReLU function will imported on the first layer of the input data. Then it will again define assign it x. Then again the ReLU function will import it on the second layer of the data. So the all computation will be done according to these libraries. So we don't have to define manually everything here. So now this is the definition of get weights of model. This definition is to extract the weights what we have got after the training of model using the algorithm. So it will the parameters, model dot parameters will extract the parameters from model, but it will take every component of this parameter, this loop for p in model dot parameters, and add it in the all component will concatenate, and it will detach, so it will not take and add up to the previous component, and it will make a 1D array of all model parameters. Then we have defined set weights, which has argument, model, and weights here. We have defined a variable which is equal to 0 here. So for parameter in model dot parameter, let's take we have 2 parameters in our model, W1 weight matrix and W2 weight matrix. Then we will calculate the shape of this W1 matrix. Let's assume it is 2 cross 3 matrix. So we have shape of 2, 2, 3, and size is param dot. This function will calculate all the components of the parameters. Like if W1 is 2 cross 3, then it will give us 6 number. So size of the parameters will provide number of all components in a parameter. Then in parameter dot data will assign by a tensor. It will take the first weight parameter from offset is 0 here, 0 to size, like 0 to 6 element. It will slice the 1D array. We have defined 1D array here. It will take only first 6 element and reshape it into the shape of W1, let's say, and again it will convert into the float variable, which is standard for the neural network. Again, offset will add up by the size. So again, we will take second parameter of we have taken 6 to 12 again. So that's how we will set the weights W1, W2, W3 like this. Then we have defined the fitness function. So fitness function will take the model weights X and Y. Fitness value is generally the objective function of our problem. So in neural network, the objective function is loss function. So set weights, first get the weights from here. We will get the weight parameters in a vector or matrix form from set weights, and with torch dot no grade will ensure that there is no need to compute gradients. In earlier code, we have provided required gradients. Because we have required the gradients from torch library, here we are using a metaheuristic algorithm, so we don't need the gradients. So we have defined it. So, and now output variable will take the input data in model. Then model X will return the data after last layer. And loss function will be cross entropy. Here we have taken f dot because we already imported torch.nn functional as f. It has the cross entropy function, and out y will two variables in the cross entropy function. It will also define the softmax values of the output parameters. That's why we doesn't define softmax here, because it is a multi-class problem. And again, we will compute the accuracy to monitor the progress. And out.argmax1 gets the predicted class for each output. It will define that it is equal to y or not. If it is equal to y, it will take the mean of every item as a float, which is the accuracy. Accuracy is the mean of correct predictions. So it will return the loss and accuracy. The dot item will return it as a float variable, because we have used the loss again and again. So that's why we have taken as dot item. Then we will define the train function of genetic algorithm. The model class is a parameter, which is the model. X is the input data, Y is the target label, population size 20, and generations are 10 here. So model will assign by the model class, the model provided here. Then dimension will calculate the all number of parameters, because for P in model parameters, this function will calculate all number in a single parameter. I already told it. So it will sum up all the numbers. That means in the whole architecture of the neural network, what number of parameters we have needed. So the dimension will define that. And again, the population. So population will define as a normal distribution of random matrix of population size and dimension. Like let's assume the dimension is 30. We want 30 all parameters for the whole architecture, and this is 20. So the this variable will be a matrix of 20 cross 30, and these are the list, loss tree, and accuracy tree. So for loop for generations are 10 years. So we will go for the first generation now, and scores will be compute the fitness model. So here we will go in the pop matrix, we have defined it. It is 20 cross 30, let's say. Then we want 30 parameters. So every value, every index of this matrix will be a solution for our optimization problem. So we will take every solution by this index IND, and we will define in the fitness function. Fitness wants weights. Weights is the solution of this optimization problem, which is a fitness value. So it will compute the fitness value for every solution appeared in random population. For every random solution, it will compute the fitness value. Then we will compute the losses. Losses will take as an array for S in scores. We will take the first entry because fitness function will return loss and accuracy. So it is a 2D matrix. So we will take the first entry, which is loss only for S in scores. Scores have loss and accuracy because fitness return loss and accuracy, and accuracy will be an S1 for S in scores. So for the best solution, we will arrange the losses. We will take the minimum loss from losses here. We have different losses for every solution in this pop variable. So we have arranged, we will compute the minimum loss from these losses, and it will assign into the best IDX, which is the best index for the loss, and it will print the generation +1 will be taken because JEN will start from 0. We want to print it as a generation 1. So that's why we have taken +1, and loss is the lowest loss is for best IDX. So we will provide the index here in losses, and accuracy is also for the same index. It will take up to the 4 values after decimal, and loss tree will be added by this lowest loss. So we have one entry in this loss tree now, and accuracy will also add up by this best accuracy. Now we will take a new variable top. We will sort the losses in an ascending order. The lowest will be first, and we will take only those entries, only 50 entries, because we will slice this matrix by this colon population size divided by 2. That means we will take only 50% population from the parent population of lowest loss. We will arrange the losses in ascending order. Then we will take only the top 50% losses and take the indices from it, and we will take the solution of variable of these 50% solutions. And then we will define a empty list of children. So for in range of these 50% population, we will do mutation and crossover. And for crossover, we will choose 2 parents from this top population randomly. So the length of it will taken from the length of top, and size will be 2. So it will take only 2 solution from the top matrix. And crossover, where np.where the random number will generated of dimension. We have chosen 2 parents randomly. Now we will see, we have to assign P1 or P2. It will be done by the uniform crossover, where if it is greater than 0.5, then P1 will go, and if it is not, then P2 will go. Now, cross has either P1 or P2. Then child variable will be assigned by the cross plus some Gaussian noise, which is between 0.0 to 0.1 to increase the diversity in the algorithm. And this empty list will be added by this child matrix here. So this array will be added in this list. Now we will stack these population solutions by np.vstack. So it will concatenate top 50% parents and 50% new children. It will top has only 50% of solution, and children also have 50% new solutions. Now, pop as the dimension we have defined earlier. Yes. So we have to take as it is 20 cross dimension. Now it has the same dimension as 20. We have taken the 50% older solution and 50% latest solutions. Now we can get the best weights. So for the solutions in the pop variable, which has the vectors of solutions, we will compute the losses and take the minimum loss, and best solution of weight vector will be assigning best weights, and model will be redefined for the next generation, but the weights will be remain same, and set weights will be called for this thing. Set weights will be written the parameters as a matrix, as in a shape. Here we have parameter in a vector shape only. Now we have in a matrix shape. So we can expect final weight matrices. So this variable will be assigned by the list of model parameters. List will create a list for these parameters, and so the first parameter will be the W1. We have 3 layer here. So we have 3 weight matrices and 3 bias. And first entry will be converted into NumPy array. And second entry also third, fourth, fifth, sixth. We will print it. Then it will return the loss history and accuracy history for the first generation. Again, this thing will done for the second generation. So this is the definition of function of train-GA. It has 3 arguments. Population size and generation already defined. So we will insert the arguments in this function. Loss tree, accuracy tree will be written. So it is equal to train-GA. Net is our class of neural network. We have defined here net. This is the function. This is our model net, and X train, Y train. So it will this line will compute all this, because we have already defined these things in the function definition, and the loss is decreasing according to generations and accuracy is increasing. So these are the final optimal weights and biases as in 1D array. These are in the 1D array before, but after providing the set weights, it is in the matrix form. So now we can plot the loss tree and accuracy tree according to generations. So the same code for the plotting of the data of loss and accuracy. You can see according to generation, loss is decreasing and accuracy is increasing. So this is the thing for get the best parameters using genetic algorithms. Now we will see how can we apply PSO, particle swarm optimization, to use to extract the best parameters for our network. So all the definitions have defined earlier, and the fitness definition is also same. Tag weights is defined already, and these things, this will calculate accuracy, this will return the loss and accuracy, the fitness value. So we will define the definition of PSO. It will take the model X input data, Y swarm size, which will be the population of swarm. We will take 20 swarms for this computation, and generation will 10. W is the weight of inertia. If you remember the formula of the PSO, W is a constant. We have taken it as 0.5, and C1, C2 are the coefficients. So it will return global variable of W1 best, V1 best, W2 best, and these things. Now model will define by assigning the model class, and again dimension will be calculated using this function. So dimension is the all number of parameters used in the model architecture. Now again assume the dimension is 30 and we have swarm size of 20. Then swarm is a matrix of 20 cross 30, and every row is a solution of our fitness function, and we have to see which solution will minimize the fitness value. And again, velocity, we have to compute the velocity for PSO also. So we will compute the velocity using, initialize the velocity using the zero matrix. Like so means it will take the size shape as it is, as swarm have. So swarm variable has 20 cross 30. So it will also have 20 cross 30 size. And personal best, in PSO, we have two types of minima, personal best and global best. And personal best will first at first it will copy as it is the swarm matrix, and then personal best scores will be computed as an array. So the fitness for P in personal best. So personal best is a matrix of 20 cross 30. So for every row, the fitness value will be computed, and it will take as an array. So global best is the lowest. It will return loss because we have taken 0 here, because fitness value will return two things, loss and accuracy. But to minimize, we have to minimize the loss. Accuracy is only for the monitoring. So we will assign 0 here to only take the loss here. And personal best, the index of the lowest loss, personal best will be the solution of global best. And again, loss history and accuracy history is an empty list. So now we will start our generation in generation loop. For generation in range of generations are 10 here, and for I in range of swarm size. So for every value of swarm size is what? Swarm size is 20. For every I equal to 1 first, it starts from 0, but we will assume it is 1 for the first entry of swarm size. And loss accuracy will be calculated by the first swarm, and swarm has the rows as a solution of this problem. So I will be the first row of SOM matrix. It will calculate the fitness value as loss and accuracy. Now, for all the SOM matrix, which is a random matrix, we will compute the personal best score. So, if loss is less than the personal best score for this index, like zeroth index, then we have not find our global best, because loss is less than our for this solution than this solution. Then we will assign the personal best for this index the SOM solution. So the personal best scores for this index is equal to loss. So now we will compute this for whole SOM size for 20 SOMs. Now we have scores for 20 SOMs, and global best will be the minimum from the personal best scores. So the minimum which solution will give the minimum fitness value will be the global best. Now we have to update velocities and positions. R1, R2 are the random vectors in PSO formula. It also has the same size, like SOM size and dimension. And velocity will be W star, W multiplied by velocity, which will initialize by as same as SOM matrix. And C1 R1 personal best minus SOM position plus C2 R2 global best minus SOM position. We have to update it by this formula. This is representing the position of SOM. This will be updated by adding the velocity. If you remember the formula presented in previous presentation. So best loss and best accuracy will be from the global best. So the fitness value will be calculated for the global best, and history list and accuracy will be added up by these things for every global best of for each generation. So this is for first generation. We have got the global best. So the history loss history list and accuracy history list will be added by these things, and we have to print for generation 1 loss is this best loss, and accuracy is this best accuracy, and again we have to define the model class, which will assign, and set weights, which is the definition is already defined, which will take the weights as of the shape we have required, and parameters. Model dot parameters will create a list of model parameters, and W1 best will be take the first element of this list, and it will convert it into a NumPy array, and this will print the optimal weights and prices here, and it will also print our plot of loss history and accuracy history. So these whole things are in only one definition, which is train PSO. Now we have defined all these things. Now we have to do just write one line train PSO, put the argument of neural network model, net, xtrain, ytrain. Then whole computation will be done by this definition, and the print for the 10th edition of loss and accuracy will be shown, and again the final weights and parameters, and the plot will also be printed because plot is also in the definition. So you can use these best parameters in your further computation for classifying the data and tasks. So please let me know if you have any doubt in these codes.
Participants, if there are any doubts, please post in the chat box.